Hello everyone. Today we will start few more problems on losses of pre-stress. So today's first problem: a pre-tensioned beam 250 mm wide and 300 mm deep is pre-stressed by 12 wires each of 7 mm diameter, initially stressed to 1200 Newton per mm square with their centroid located 100 mm from the soffit. Estimate the final percentage loss of pre-stress due to elastic deformation, creep, shrinkage, and relaxation of stress in steel using IS 1343 code and with the following data. Relaxation of stress in steel 90 Newton per mm square, ES, that is Young's modulus of steel, 210 kilonewton per mm square, and EC, Young's modulus of concrete, 35 Newton per mm square, creep coefficient 1.6. So in this problem we need to calculate loss due to elastic deformation, creep, shrinkage, and relaxation of stress in steel. So relaxation of stress in steel, it is directly given in question, that is 90 Newton per mm square. So no need of calculation at all, you directly consider the same value. And remaining 3, elastic deformation, creep, and shrinkage, for these 3 we need stress in concrete at the level of steel, that is sigma c value we need to calculate, and it is given 12 wires of 7 mm diameter located at 100 mm from the soffit, that means from the bottom of the beam. Overall cross section is 250 mm wide and 300 mm deep. So from figure we can see the eccentricity is 50 mm. So depth of the beam is 300. For the beam, its centroid will be at 150. From bottom it is 100 mm. So we need 50 mm as the eccentricity. Area of cross section, moment of inertia, and pre-stressing force, it is stress in steel into area of steel. Stress in steel, it is 1200, and area is area of 7 mm diameter wires of 12 numbers. Then eccentricity, since it is a straight tendon, both E and Y will be same. Substitute in the formula P by A plus M by I into Y, we will get sigma C value. Modular ratio ES by EC, we will get 6. So first, loss due to elastic shortening, alpha E, that is modular ratio into sigma C, we will get 59.1. Loss due to creep in concrete, here creep coefficient is given, so you need to go with creep coefficient method, that is creep coefficient into modular ratio into stress in the level in the concrete at the level of steel, that is sigma C. So phi is 1.6, modular ratio 6, and sigma C is 9.85. We will get 94.56. Then loss due to shrinkage strain, since it is pre-tensioned, as per IS 1343 for pre-tensioned members, shrinkage strain will be 0.0003 and ES, so it is 63. And relaxation of stress, it is directly given 90 Newton per mm square. Add all the losses, we will get total loss 306.66 and calculate the percentage with respect to 1200 Newton per mm square. So that is 25.55%. Next problem: a post-tensioned pre-stressed beam of span 10 meter has a rectangle cross section 300 mm wide and 800 mm deep. The beam is pre-stressed by a parabolic cable concentric at the supports and with an eccentricity of 250 mm at the center of the span. So it is parabolic profile. The cross section area of high tensile wires in the cable is 500 mm square. The wires stressed by using a jack at the left end, so that initial force in the cable at the right end is 250 kilonewton. Using the following data, calculate total loss of pre-stress in the wires, the jacking force required at the left end. These two things we need to calculate. Use the following data. Coefficient of friction for curvature effect, it is 0.55. friction coefficient for wave effect 0.003 per meter, anchorage slip at jacking end 3 mm, relaxation of stress in steel 4%, shrinkage of concrete 0.0002, creep coefficient 2.2, modulus of elasticity of steel 210 kN per mm square, and same of concrete is 35 kN per mm square. So here it is post tension and you need to find out total loss, and you are applying a stress, where it is the total loss of stress and jacking force required at the left end. Okay, so first, since it is parabolic profile, we need to find out sigma c value. So since it is parabolic, sigma c at support and sigma c at midspan we need to find out. For that we need slope. Slope is first derivative of the equation of parabola. So we will get theta a this is frictional loss, (250 kilonewton). It is given, where it is, the initial force in the cable at the right end, that is the end where you are applying the stress, is 250 kilonewton. Sorry, the force at the right end means you are applying force at left end, and at right end you have force of 250 kilonewton. So if you want to maintain 250 kilonewton at right end, what should be the force you need to apply at left end? You have to calculate. So for that we use this equation, friction equation first. So we will get alpha, slope is 0.1 radians, so alpha will be theta a plus theta b since it is parabolic. Friction coefficient 0.55, wave coefficient is given, x is 10 meter, that is span of the beam. Substitute in the equation, we will get initial stress, that is jacking stress. Then initial pre-stress, here P naught is the force, we need to find out stress. So load by area of the steel 581.38 Newton per mm square. Next, loss due to creep in concrete, here creep coefficient is given, so we need to go with creep coefficient method only. Then to calculate we need also stress in concrete, so sigma c elastic shortening of concrete. Since it is post tension, there is no loss due to elastic shortening. Loss due to shrinkage, then relaxation of stress, it is 4%. Here loss due to friction, you can take the difference also. Loss due to anchorage slip, so total loss and percentage loss. Next problem, a pre-tensioned beam of rectangular cross section 150 mm wide and 300 mm deep is pre-stressed by 8 number of 7 mm diameter wires located at 100 mm from the soffit of the beam. If the wires are initially tensioned, a stress of 1100 Newton per mm square, calculate the stress in steel at transfer and effective stress in steel after all losses, given the following data. So relaxation of stress in steel, shrinkage of concrete, creep coefficient, up to time of transfer 35 Newton per mm square, total after all losses it is 70 Newton per mm square, shrinkage 100 into 10 power minus 6, 300 into 10 power minus 6, creep coefficient 1.6. So here in this problem we have two conditions. Calculate the stress in steel at transfer and effective stress in steel after all losses. So that means here we need to consider immediate losses and time dependent losses. So first we will calculate the required data. So area is given, moment of inertia we can calculate, area we need to calculate. Then P, stress in steel into area of steel, we will get force. Then sigma C we need to find out, P by A plus M by I into Y. Since it is straight tendon, E and Y both will be same, sigma C. Modular ratio ES by EC, we will get this. Then loss of pre-stress at transfer, that means immediate losses, the losses which come under immediate losses. One is elastic shortening, relaxation of stress in steel. It is both, it will come under immediate loss and time dependent loss. Then shrinkage, it also come under both, and loss due to creep, it is time dependent. So first, loss due to elastic shortening, modular ratio into stress in concrete at the level of steel. Then loss due to relaxation of stress in steel, it is directly given as 35 Newton per mm square. Then loss of pre-stress due to shrinkage strain is given, and Young's modulus of steel is given. Then loss due to creep, it is 0, since there is no creep coefficient is 0 in the data. So add all three, we will get total loss. Then stress in steel at transfer, initial stress what have applied minus total loss, we will get 977.1 Newton per mm square. Same way, remaining stresses we need to consider. Loss of pre-stress after all losses, due to elastic shortening it will remain same. Then loss of pre-stress due to relaxation of stress, it is also directly given, 70 Newton per mm square, take as it is. Loss of pre-stress due to shrinkage strain is given, take it and simplify, we will get 63 Newton per mm square. Creep coefficient is given, so we need to go with creep coefficient method. Alpha into modular ratio 6.67 into sigma C. We will substitute the values, we will get 107.04 Newton per mm square. Add all the losses, we will get 306. So stress in steel after all losses, it is 793.06 Newton per mm square. That's it. So next problem, a pre-stressed concrete pile 250 mm square contains 60 pre-tensioned wires, each of 2 mm diameter, uniformly distributed over the section. The wires are initially tensioned on the pre-stressing bed with a total force of 300 kilonewton. Calculate the final stress in concrete and the percentage loss of pre-stress in steel after all losses, given the following data: ES, Young's modulus of steel, Young's modulus of concrete, ultimate creep strain, shrinkage strain, relaxation of stress in steel. Since all wires are uniformly distributed in the cross section, eccentricity will be 0. See, if you take the square, you have 60 wires. So 60, you need to distribute all 4 sides. Distribute about all 4 sides, since it is uniformly distributed in the cross section. So all 4 sides you need to distribute. So that means if you take the centroid of the distributed wires, it will coincide with the centroid of the cross section of the beam or pile, concrete pile. So eccentricity is 0. Stress in concrete at the level of steel, since eccentricity is 0, Y will also be 0. So it is only P by A is sigma C is 4.8 Newton per mm square. Alpha E modular ratio, initial stress in steel, pre-stressing force upon area of steel. We have 60 wires of 2 mm diameter, so it is 1591.55 Newton per mm square. Then loss due to elastic shortening, modular ratio into sigma C. Loss of pre-stress due to creep, ultimate creep strain is given, so need to go with ultimate creep strain method. Substitute the values, we will get 30.24 Newton per mm square. Loss of pre-stress due to shrinkage of concrete, Shrinkage strain is given, Young's modulus of steel is given. Loss of pre-stress due to relaxation of stress in steel, it is given 5% of initial stress, so 5% of 1591.55 Newton per mm square. So add all the losses, that will be total losses 183.29, then take the percentage. Then initial pre-stressing force is 300 kilonewton. What is the final pre-stressing force? Initial pre-stressing force minus pre-stressing force due to all losses of pre-stress. So initial pre-stressing force you have applied, final pre-stressing force means the force which remained at the other end. So again the stress you have calculated, that you need to find out. So the loss of pre-stress you have calculated, total loss, it is 183.29. If you take the cross section, what is the stress or force lost in it, we come to know. So if you minus it with initial pre-stressing force, we will get 265.45 kilonewton. So final stress in concrete, final pre-stressing force by area of cross section, that is 4.24 Newton per mm square. Then next problem, a post-tensioned pre-stressed concrete beam of 50 meter span is subjected to a transfer pre-stress force of 9.38 mn, that is meganewton. The transfer of force is at 28 days strength. Profile of the cable is parabolic with maximum eccentricity at midsection as 1100 mm. Determine the loss of pre-stress and find the jacking force required. The beam is subjected to live load of 24 kN per meter and jacking is done at both ends of the beam. The data is given as below. Initial pre-stressing force, it is once again it is given 9.38 mn. Area of concrete section, area is directly given, you should remember. Area of steel you are using. Then moment of inertia is also directly given. Anchorage slip 2.5 mm per anchorage, remember this. Loss due to relaxation of steel 2%, creep coefficient 1.2, friction coefficient 0.25, wobble coefficient 0.0015 per meter. Modulus of elasticity of concrete 38.2 GPa. Modulus of elasticity of steel is 210 GPa. Take density of concrete as 24 kN per meter cube. Okay. So here it is post tensioned beam. So we need to find out losses of post tension. That is all losses we need to find out. So P is given in meganewton. Mega is 10 power 6. So 9.38 into 10 power 6 Newton. Live load is given 24 kilonewton per meter. Here loads we need to consider additional. So dead load, area of cross section into density of concrete 22.73 kilonewton per meter. Here 10 raised to minus 6 is converting mm square to meter square. W total load, WL plus WD, dead load plus live load, we will get this. And moment due to both dead load and live load, M. Then eccentricity, since it is parabolic and eccentricity will be common, 1100 mm. Since it is parabolic, to calculate stress in level in concrete at the level of steel, we need to find out at both ends, at the support as well as at the mid span. So eccentricity will be 1100 mm. At support, eccentricity we need to consider as 0 and y will also be 0, and at mid span eccentricity and y both will be 1100 mm. So at support P by A will remain because P by I into y, here both E and y are 0, M by I into y, y is 0, so we remain with P by A. Stress in concrete at the level of steel, we will remain with all coefficients, all the values. So by simplifying, we will get 2.336 Newton per mm square as the midspan stress and 9.904 Newton per mm square as the support section, and by taking average of both, we will get 7.38 Newton per mm square. So then loss due to anchorage slip, ES delta by L, 10.5 Newton per mm square. Initial pre-stress P by AST, area of steel, because stress we need to consider for further calculations. So 1050 Newton, 0.4 Newton per mm square. Loss of pre-stress due to relaxation of stress, 2% of 1050 Newton per mm square. Loss of pre-stress due to creep of it is creep coefficient is given, so creep coefficient method, 5 into alpha E into sigma C. Then loss due to friction, mu is given, K is given, X it is 50. Loss of pre-stress due to friction, it is 125 Newton per mm square. Since the tendon is tensioned from both ends, both sides, loss of pre-stress should be reduced to 50%. Here you can do it with two ways. One thing, you can take total loss by 2, or you can go with span, you can consider as 25, and alpha what you have calculated, you can take it for only 1. Sigma theta A is 0.088 and theta C you can consider, and midspan, and it will be considered as 0. Both ways you can do. And loss of pre-stress, total loss you can consider percentage loss of pre-stress you can do. Then jacking stress, initial pre-stress plus. So total initial pre-stress what you have applying, and what is the total loss. If you add both, what should be the force you need to apply, you will get jacking stress, that is 11.59.82 1159.8 Newton per mm square. Then again multiply it with AST, we will get jacking force. Next problem, a pre-tensioned pre-stressed concrete sleeper 300 mm wide by 250 mm deep is pre-stressed by using 4 wires of 7 mm diameter. Wires are located at top and 5 wires near the soffit. The effective cover being 40 mm. The initial stress in the wires is 1256 Newton per mm square. Assume the modular ratio as 6. Estimate the percentage loss of pre-stress in the top and bottom wires due to elastic deformation of concrete. So at top you have 4 wires and at bottom you have 5 wires. The depth of the sleeper is 250 mm. So first you need to find out what is the centroid of the cables or tendons. With respect to bottom, it is 115.56. So y1, y2 we have to calculate, same as the beginning problems. Then total overall eccentricity is 9.44. Area E, I, moment of inertia. Here y1, y2, that will differ while calculating loss due to elastic shortening. Y1, y2 will differ. So first we will consider top layer. Both y1 and y2 both will remain same because the effective cover is 40 mm at top as well as at bottom. So with respect to S centroid distance, it will remain same. So no need to bother. Sigma C we have calculated. Loss due to pre-stress, alpha E, modular ratio into stress in concrete at the level of steel. percentage loss of stress. Due to elastic is substitute the values, that is top tendons and this is bottom tendons. You will get total loss. Thank you.